Welcome to today's paper reading. Today's paper is titled, RLHF Workflow, From Reward Modeling to Online RLHF. This paper was published on the AR14 preprint by Hanze Dong and colleagues from Salesforce AI Research and the University of Illinois Urbana-Champaign. This technical report introduces the workflow of Online Iterative Reinforcement Learning from Human Feedback, RLHF, which has been shown to outperform its offline counterpart significantly in recent literature on large language models, LLMs. The report aims to bridge the gap by providing a detailed, reproducible method for online iterative RLHF. Given the infeasibility of online human feedback for open-source communities with limited resources, the authors construct preference models using diverse open-source datasets to approximate human feedback. The report also discusses the theoretical insights and algorithmic principles behind online iterative RLHF, followed by a practical implementation. The trained LLM, Llama 3-8 BSFR iterative DPOR, has achieved impressive performance on various LLM chatbot benchmarks and academic benchmarks. The models, datasets, and comprehensive code guidebooks are made publicly available. Reinforcement learning from human feedback, RLHF, is a crucial technique for integrating human preference signals into machine learning methods, especially for aligning large language models, LLMs, with human values and preferences. Notable examples of RLHF applications include closed-source models like ChatGPT, Claude, and Gemini, as well as open-source models such as Zephyr, Starling, and Llama 3. Since the introduction of ChatGPT, RLHF has attracted significant interest across various communities. However, RLHF remains relatively underexplored within the open-source community compared to supervised fine-tuning methods. To facilitate our discussion, we build upon the standard RLHF workflow, characterizing an LLM by a policy pi that takes a prompt X and produces a response A. The initial model pi 0 is fine-tuned on instruction following data after the pre-training stage. The key component in RLHF is the preference oracle, which mathematically defines the preference signal. Despite its potential, RLHF faces challenges such as being underexplored in the open-source community, computationally expensive fine-tuning processes, and significant GPU memory pressure due to the need to load multiple LLMs simultaneously. Figure 1 provides a simplified illustration of the reward modeling and online iterative reinforcement learning from human feedback, RLHF, process. The policy model, which represents the large language model, LLM, being aligned, generates two responses, A1 and A2, for a given prompt X. These responses are then evaluated by the reward model, which assesses their quality based on the preference data collected from human feedback, or a proxy model. The reward model updates its parameters to improve the policy model's performance. This iterative process continues, with the policy model generating new responses, the reward model evaluating them, and the parameters being updated accordingly. This cycle helps in aligning the LLM with human preferences more effectively. Table 1 provides a comprehensive summary of various open-source preference datasets used in the study. It highlights the average lengths of prompts and responses, distinguishing between preferred and rejected lengths. The table also notes the source of the text completions and the pre-processing techniques applied to ensure data quality. This summary is crucial for understanding the characteristics of the datasets used in preference modeling and reward learning tasks. In this section, we detail the construction of preference models, focusing on reward modeling as the maximum likelihood estimation, MLE, of the Bradley-Terry, BT, model and the general preference model. We utilize a mixture of open-source datasets for training, including HHRLHF, SHP, and HelpSteer. The reward model, based on Llama 3-8B, is trained for one epoch with a batch size of 512 and a learning rate of 2 × 10⁻⁶, employing a cosine learning rate schedule. For the Gemma 2B model, a larger learning rate of 10⁻⁵ is used. Evaluation results show that the preference model outperforms the BT model, especially in reasoning tasks related to coding and math. This performance improvement is attributed to the inclusion of more data, particularly in coding, math, and safety. Figure 2 provides an illustration of the Bradley-Terry, BT, model and the preference model. The BT model is a statistical model used to represent the probabilities of the outcomes of pairwise comparisons. The preference model, on the other hand, is a broader concept that encompasses various methods for modeling preferences between alternatives. This figure visually represents these models, aiding in understanding their structure and application. Figure 3 provides a detailed view of the training record for reward modeling. The figure is divided into 3 sections, each displaying a different metric crucial for understanding the training process. On the left, the training loss is shown, which is a measure of how well the model is learning from the data. In the middle, the gradient norm is presented, indicating the magnitude of the gradients used to update the model's parameters. On the right, the learning rate is depicted, which controls the step size at each iteration while moving toward a minimum of the loss function. These records collectively offer insights into the optimization process and the model's performance during training. Figure 4 illustrates the training record of preference modeling, detailing the training loss, gradient norm, and learning rate from left to right. The Llama 3-8B base preference model was trained with a global batch size of 128 and a learning rate set to 5 × 10⁻⁶, employing a cosine learning rate schedule with a warm-up ratio of 0.03. Table 2 presents a detailed comparison of the test accuracy between the Bradley-Terry (BT) reward model and the preference model, evaluated using the reward bench. The table highlights the performance of different base models across various data mixtures and categories such as chat hard, safety, and reasoning. Key findings include the preference model's superior performance in reasoning tasks and the positive impact of additional data, particularly in coding, math, and safety, on the BT model's accuracy. Figure 5 presents a heat map illustrating the Pearson correlation coefficients between the reward and the length of responses. For each prompt, the SFT model generates 16 responses, and the correlation coefficient is calculated. The prompts are grouped by the mean response length on the y-axis. The left heat map corresponds to the UltraRM13B model, while the right one represents our BT reward model based on Mix2. In this section, we discuss the development of the main algorithms for online iterative RLHF, focusing on both theoretical insights and practical implementation details. We start with supervised fine-tuning, SFT, where we use the Llama 3-8B model as our base. The training is conducted for one epoch with a learning rate of 2 × 10⁻⁵, employing a cosine scheduler with a global batch size of 32 and a warm-up ratio of 0.03. To enhance training efficiency, we utilize a block size of 8,192. Moving on to iterative direct preference learning, we introduce a hybrid batch learning framework that combines offline and online data, featuring a non-symmetric structure to balance exploitation and exploration. We provide theoretical guarantees for strategic exploration methods, ensuring efficient and stable training. Finally, in practical implementation, we approximate the MLE policy using DPO and discuss the selection of an exploration policy, including techniques like temperature tuning and rejection sampling to introduce diversity and facilitate exploration. Figure 6 illustrates the implementation of our iterative direct preference learning framework. At the first iteration, t = 1, the historical dataset is empty, and the resulting policy model MLE is identical to its initialization, which is the SFT model checkpoint pi0. As the iterations progress, the historical dataset expands with preference data collected from previous iterations, leading to updates in the policy model MLE. The evaluation of the models is conducted using standard benchmarks such as Alpaca Eval2, MTBench, and ChatArenaHard. Alpaca Eval2 focuses on single-turn conversations with 805 test prompts, while MTBench is a multi-turn benchmark with 160 prompts. ChatArenaHard consists of 500 prompts from live data, evaluating various aspects of the model's capabilities. Additionally, academic benchmarks like GSM8K, MLU, Human Eval, Truthful QA, ARC, and MBPT are used to measure the model's abilities in coding, reasoning, and general knowledge. These evaluations are crucial for understanding the impact of iterative RLHF on specific aspects such as reasoning and truthfulness. Table 3 provides a summary of the benchmarks used in this project for evaluating large language models, LLMs. It lists the metrics and the number of shots, which indicate whether the evaluation is zero-shot learning or in-context learning. The benchmarks include datasets such as LC Alpaca Eval 2, MTBench, GSM8K, and MLU, with metrics like win rate, score, and accuracy, ACC, being used. The number of shots varies, with examples being 0 for zero-shot learning and 25 for in-context learning. This table is crucial for understanding the evaluation methods and their implications for LLM performance. Figure 7 provides a visualization of our prompt collection using Nomic Atlas. The left figure is color-coded based on the data sources of the prompts, offering a clear distinction between different sources. The right figure is color-coded by topics, which are automatically generated by Nomic Atlas's custom topic model. This visualization helps in understanding the distribution and categorization of prompts, aiding in the analysis and selection process for further experimentation. Table 4 presents the evaluation results of various models across different benchmarks, highlighting the performance of our 8B model in comparison to other models, including those with larger parameters. The table includes metrics such as the length control win rate on Alpaca Eval 2, scores on MTBench and Chat-Arena-Hard, and a comparison with models based on different architectures and training methods. Notably, our model trained with iterative DPO outperforms the vanilla DPO baseline and several larger models, demonstrating the effectiveness of online iterative RLHF in improving conversation quality. Table 5 presents the evaluation results of our model on academic benchmarks, comparing it with other open-access large language models, LLMs. Key metrics include performance on GSM8K, MLU, Human Eval, Truthful QA, ARC, and MBPP. Notably, our iterative RLHF model shows improvements over the SFT baseline in several benchmarks, indicating effective alignment and leveraging of pre-training capacities. Table 6 presents an ablation study examining the effects of different reward models and the introduction of a length penalty in the Online Iterative Reinforcement Learning from Human Feedback, RLHF, process. The study reveals that the length penalty effectively mitigates the tendency of models to produce overly long responses, as evidenced by the reduction in average response length when compared to models without this penalty. Notably, the UltraRM13B model, despite its stronger bias towards longer responses, achieves a higher win rate in the Chat-Arena-Hard benchmark, suggesting a potential verbosity bias in this particular evaluation context. The model trained with the length penalty not only produces shorter responses but also demonstrates superior performance in terms of the Alpaca Eval 2 win rate and on certain academic benchmarks, highlighting the benefits of addressing length bias in reward modeling. In this report, the focus has been on the workflow of online iterative RLHF, which uses on-policy sampling and external preference signals. The model, Llama 3-8 BSFR iterative DPOR, shows strong performance on benchmarks. However, there are several areas for future exploration. Firstly, the quality of the preference signal is crucial. Currently, a proxy scalar reward model is used, but exploring multi-head reward strategies could be beneficial. Secondly, while rejection sampling is effective, developing more advanced exploration strategies is an open challenge. Lastly, RLHF models often produce longer responses, which can be mitigated by additional algorithmic designs or post-training techniques. The hope is that these findings will contribute to the development of stronger open-source LLMs. Thank you for watching.